Hello everyone, I am Snigdha Bharadwaj, Assistant Professor, ITS College of Pharmacy. I welcome you all in my session. So, in this session we are again going to discuss about a one compartment open model for extravascular administration. So, let us start. So, in earlier session of the same topic extravascular administration, we have discussed about various parameters and factor affecting of extravascular administration, along with that zero order and first order kinetics. So, when we talk about oral administration, because in extravascular, rectal, oral and many more administration comes under extravascular administration. So, here if we talk about oral administration of unchanged drug in blood and plasma, because we are calculating the amount of drug in blood and plasma, right. So, we if we talk about for oral administration specifically, so first the dose or drug, the absorption site will be lumen, right, GIT stomach, and then it will get absorbed from the site of absorption and reaches to systemic circulation and then distributed all over the body tissues and bloods and then eliminated from the system. So, when we talk about oral administration of unchanged drug in blood and plasma, so the value will be like XO, X naught we can say, Ka, Ka is the absorption rate constant, X is equal to VDC, Vd means volume of distribution, apparent volume of distribution, and C means the drug concentration, C means the basically the drug present in blood plasma. So, K is your elimination rate, where XO is an oral dose of the drug administered and X is the amount of drug in the body. Ka and K are the first order rate kinetics constant of drug absorption and elimination. That means, this is the absorption rate constant and this is the elimination rate constant. For a drug that enters the body by an apparent first order rate absorption process and is eliminated by first order process only and distribute in the body according to one compartment model. Basically, we are talking about only one compartment modeling for all the IV infusions, IV bolus administration and extravascular administration. So, do not get confused whether it is two compartment or one compartment. In this unit third, we are only covering the one compartment modeling for all these subtypes. Although you in your syllabus, I think in unit 4 there will be discussion about two compartment modeling as well for IV bolus and IV infusion, but here in unit 3rd we are only discussing about extravascular or one compartment model for extravascular, IV bolus administration and IV infusions. So, if we talk about oral administration, so you can see that this equation will be followed and drug enters the body by using first order absorption and then eliminating from the body using first order elimination process. So, here we can say that the rate of drug change in the body is equal to rate of drug absorption minus rate of drug elimination. So, rate of change, how the drug rate is getting changed, it is basically the rate of drug absorption minus rate of drug elimination will give you the value of amount change of drug in blood plasma, where the equation will be dx by dt is equal to dxa minus dxc by dt, by simplifying this, dx by dt is equal to ka xa minus kex, where xa is the amount of drug available at the absorption site, the drug which is ready to be absorbed from in the blood. Let us assume that f is the fraction of oral dose xo that will be already absorbed and present in blood. So, that fraction is considered to be ready to be eliminated as well, because it is already absorbed and present in systemic circulation. Once it reaches to systemic circulation, we can say the drug is ready to be eliminated through the system, right. At time 0, Fxo amount is available for absorption Therefore, x a naught is equal to f x o. So, x a naught is amount of drug available for absorption at time t 0. The rate of disappearance of the drug from the GIT is given by dxa by dt is equal to minus Ka xa. So, basically this is constant dxa by dt. So, if we replace dxa by dt K xa, the time or course of the amount of drug in the body is given by x is equal to Kaf x 0. So, we replace that x a Kaf x 0. So, the equation will become x is equal to Kaf x 0 divided by Ka minus Ke e to the power k minus Kt minus e to the power Kat. So, this is basically coefficient. Dividing the above equation by the volume of distribution of drug. So, it is also called Vd, volume of distribution or apparent volume of distribution. So, x by Vd is considered C. So, C is equal to Kaf x 0 by Vd Ka minus Ke, and the remaining formula will be same, just we change the values of x and in terms of C and Vd. So, above equation describes the time course of the drug concentration in plasma following the oral route of administration. So, at larger values of the t, the above equation will reduce to C Kaf x 0 e to power minus Kt Vd Ka e, because at that in later times we generally say that the absorption rate is not much as compared to elimination rate. So, here we have replaced that Kat part of absorption coefficient. Now, above equation explains the elimination phase, that is the time when absorption no longer occurs. As I have told you just now that later periods of drug administration, we generally consider that at initial times absorption rate will be higher, but in later phases, post absorption phases or elimination phases. So, elimination phases no absorption will occur. So, finally the equation can be written in common logarithm as log C is equal to log Kaf x naught divided by Vd Ka minus Ke minus Kt 2.303. So, this will be like your final equation to be calculated. Now, determinants of absorption rate constant from oral data. So, what are the different parameters we usually identify from this oral absorption pharmacokinetic studies. So, first is method of residual. This technique is also known as feathering, peeling or striping. It is commonly used in pharmacokinetics to resolve a multi-exponential curve into its individual component. As we all know why we are discussing this compartment modeling or these arithmetic calculation, because this is our theoretical aspects and we are basically forming and designing some mathematical calculations to identify and to correlate it with the experimental data of ours. If we assess any drug concentration in blood plasma, then how we can get the appropriate concentration, whether we are calculating it right or wrong. Matching and putting those experimental data into these arithmetic calculations, we can get the desired data and we can correlate, interpret the results with the using these mathematical equations. So, we should have some basis to calculate. That is why these compartment modeling, two compartment and multi compartment, non-linear kinetics, these all are different kinds of model we use to identify various pharmacokinetic parameters. So, methods of residual basically is a technique known as feathering, peeling and striping. It is commonly used in pharmacokinetics to resolve multi-exponential curves, that means the complex curves. So, using this method we can simplify our curves to a individual components curves, right. So, the time course of drug concentration in plasma is given by equation. So, basically we are calculating drug concentration in plasma. See, but we have a variety of methods to identify the same, right. So, x by Vd is equal to C Ka f x 0 Vd Ka minus Ke. So, this value of K is obtained by using the following procedure. What is the procedure now? Plot the drug concentration versus time. You know that how it is. In this axis time is there and in this axis concentration. We plot concentration, right. So, plot the drug concentration versus time with the concentration value on the logarithmic axis. Now, calculate the slope and from the slope calculate K and elimination half life. So, we also seen that in some plots that slope value is given as Ka something like 2.303, right, divided by that K slope is Ka this and this is slope. So, this is the slope value. We can calculate the slope using this equation. So, the intercept is equal to Kaf x naught by Vd Ka minus Ke. The slope of the residual line is equal to minus Ka 2.303 as I have written here. So, this is how you can calculate the methods of using this method of residual for identifying drug concentration in plasma. Next is your Wegener-Nielsen method. So, in this method the absorption process is assumed, we are just assuming to be the first order kinetics. So, they basically this Wegener-Nielsen method is for first order for those drugs which are following first order kinetics. Understand? This method requires the assumption that the body behaves as a single homogeneous compartment, that is the single central compartment, and drug eliminated obeys the first order kinetics. That means, how much drug we are giving to the system is distributing uniformly in this within the system and getting eliminated from the system. So, Wegener-Nielsen methods follows this assumption, and on the basis of these assumptions we can calculate the drug plasma concentration. So, what will be the derivation like? The mass of balance equation can be written as the amount administered equal the amount absorbed. So, the mass of a balance equation can be written amount administered, how much dose you are administering, right, equals to the amount of drug absorbed. So, we consider it if we are giving 100 mg of dose of a drug product, that means total 100 mg is getting absorbed. So, plus the amount unabsorbed also, yes. So, if we are giving 100 mg, maybe 70 or 80% is absorbing and 30. So, total amount will be 70 plus 30, amount absorbed and amount unabsorbed. Understand? So, x naught will be like amount plus A plus AM, un, right, unabsorbed. Okay. So, the amount absorbed A to any time t is equal to the sum of the amount of drug in body x and the amount of drug eliminated from the body to any time t xc. For example, if I say that at particular time this much drug is getting absorbed and this much drug is getting eliminated, then equation I can write in the following manner, that A is your amount absorbed. So, this amount is your the amount of drug present in your blood plasma and amount of drug eliminated. So, both the values will be put here. Taking the derivatives with respect to the time gives the following equation: dA by dt is equal to dx by dt plus dxc by dt, yani ki both the absorption and elimination rate constant value we can put here, and by putting those absorption values and elimination values we can have exact amount of drug absorbed at that particular time. See this dt represent at that particular time. So, that is why we have written here. So, x is equal to VDC. So, this equation will become dx by dt is equal to Vd dc by dt, dxc by dt is equal to kx if we put dxc by dt kx, but x is equal to Vd by Vdc. Therefore, the equation will become dxe by dt is equal to kvdc. So, basically k is your absorption rate constant, Vd volume of distribution. So, the equation will become dA xc at that particular time, only the amount of drug absorbed if we talk about. So, dA by dt is equal to Vd dc by dt plus kvdc. So, after simplifying this equation, so dA the is equal to Vd dc plus kvdc dt. So, in this Wegener-Nielsen method, this equation will be used for identifying the amount of drug absorbed at particular time. So, this method tells the absorption kinetics and also the release of drug from the dosage form. So, this is how we calculate these general basically using these method of residual and Wegener-Nielsen method to identify different kinetics of drug absorption. Now, determination Cmax and Tmax. So, the time needed to reach the maximum concentration, as we have discussed from the drug plasma concentration time profile curve. So, Tmax is also important parameter, Cmax and AUC. So, those three parameters are of important concern. So, the time needed to reach the maximum concentration is called Cmax or peak time. Tmax, the time is dependent on the rate constant for absorption, that is Ka, and elimination, that is Ke. So, at that particular time Ka is equal to Ke, absorption rate is becomes equal to elimination rate. Now, at maximum time concentration, the rate of drug absorption is equal to the rate of drug elimination. So, rate of concentration change dC by dt is equals to 0, because there is no rate of change in drug in plasma, because how much drug is absorbing is equal to the elimination rate. So, the rate of concentration change can be obtained by different equation. At that particular time it will be considered as 0. So, the following equation will be followed in that case: C is equal to Ka f x naught divided by Vd Ka minus Ke E minus Kt e to the power minus Kt minus e to the power minus Kat. So, these are coefficients. Differentiating with respect to time, if we talk about specifically in how much time the drug is getting absorbed or eliminated. So, dC by dt is equal to minus k kf x naught divided by Vd Ka minus k e to the power Kt. Kt means only absorption is attaining at that particular time, plus Ka, the same equation with Kat, right. When plasma concentration reaches Cmax and the time Tmax, so dC by dt will be 0. That means no change of amount of drug will be seen if the stage will be at plateau stage, right. If it is reaching to that plateau stage, peak plasma concentration level, so no change of amount of drug can be seen. So, the equation will be like k kf x z naught divided by Vd Ka minus k e to the power minus Kt max is equal to Ka square f x naught divided by Vd Ka minus k e to the power minus Kat max. So, on simplification, the above equation, the equation will become k e to the power minus Kt max is equal to k. That means, both the sides will be equal, rate of absorption and rate of elimination. So, we can either present this equation like this, or Ka divided by k e to the power Kt divided by e to the power Kt max and max. So, this is basically how we can write it. In common logarithms, log k divided by Ka divided by K. If we are changing this equation to log, so the equation will become minus Kt max divided by 2.303 plus Kat max divided by 2.30. Therefore, Tmax the time peak time at which the concentration of drug in plasma is at its peak. So, Tmax 2.303 log Ka divided by Ke. So, substituting Tp for T, right, that point of time, Cmax is equal to Kafx naught divided by Vd Ka minus Ke e to the power minus Kt max e to the minus e to the power minus Kat max. So, this is how we calculate different parameters using the equation. The main parameters we have discussed here, Cmax and Tmax. So, once again I would like to give highlights of this session, so that you can easily remember all those important things. So, from starting in this we have discussed about oral administration of unchanged drug in blood and plasma. So, we are calculating the unchanged amount of the drug absorbed or to be absorbed or remaining to be absorbed, we can say. So, we are when we administer drug orally. So, what are the different mathematical calculations we can use to identify the drug amounts present in blood plasma. So, this is the basic equation. The x naught is equal to x is equal to VDC and the K, this is your absorption rate constant and this is elimination rate constant. So, for a drug that enters the body by an apparent first order kinetics. So, basically we are saying when we give drug through oral absorption, that is following conventional formulation, that is following first order kinetics. So, rate of drug change in the body can be calculated by identifying rate of drug absorption minus rate of drug elimination. So, at plateau point we are considering that no change of drug is seen at that plateau phase, because rate of elimination is rate of absorption. So, x is the amount of drug available at the absorption site. So, f is equal to the fraction of oral dose that will be absorbed or remaining to be absorbed from the site of action, site of absorption. At the time 0, we consider that f x amount is available for absorption and no elimination will occur at that point. So, x a naught amount of drug available at time t 0, right. So, this equation will be like in simplification. So, at the end we see that when we simplify the equation using different parameters and considerations. So, the last equation in common logarithms as written as log C is equal to log K A f x naught divided by V d by replacing x value from C V d. So, here the x is replaced, C and V d we have put minus K t by 2.303. So, for determining absorption rate constant from oral data, how you analyze the rate of absorption or constant for that particular absorption rate. So, you can either use methods of residuals using this equation or a Wegener-Nielsen method. So, both methods I have explained in detail, and now this is how also you identify Cmax and Tmax from the data as well. Cmax the point at which the concentration is it's at peak, whereas the point of time where the concentration is at peak is known as Tmax. So, both parameters can be calculated using these following equations at the end. So, these are references. I hope you understand the basic considerations of various pharmacokinetic parameter assessment using different mathematical models, and in the next session we will be continuing with the same topic. Till then, take care and stay safe. Thank you.